Okay, Susan and Mary, can you just confirm that you are seeing my slides now?
We are seeing your slides. Yep,
Okay.
and the recording is on.
Great, great. Okay, so thank you everybody for joining us on a Friday afternoon. I know by the time 2 o'clock on a Friday winds, comes around, we're getting ready to kind of wind down for the week. We have a block today from 2 o'clock to 4 o'clock. I probably won't use the entire 2 hours, and we're going to plan on taking a break maybe 45 minutes or an hour into the presentation. So this is really going to be lecture, but at the end you're going to get some pointers to my repo, additional reading, and some exercises that you can do on your own. All right, so we're going to start off with profiling code and why we would want to profile our code. So let's say you have an application, you'd like to improve the performance of it. So we're not talking about, say, a highly optimized third-party application like Amber or Gaussian, but rather, say, code that you've written yourself or something that you've developed with collaborators. And let's say that it's just taking a long time to run, and you would like to try to reduce your runtime. So there are a couple ways you could do that. One is to parallelize your code or improve the scalability. And the other is to actually look at the underlying serial algorithms and see if you could speed it up. So if we profile our code, this, first of all, gives you a way to determine what portions of your code are using the most time. So a lot of modern HPC and data-intensive applications, they comprise many thousands of lines of code. In some cases, it could actually be millions of lines of code, like the climate weather code CESM. So before you jump in and start trying to improve the performance of that code, you need to know where to spend your effort. You want to zero in on just those subroutines or functions or loops that are really accounting for the time. Next, you may want to dig a little bit deeper and find out why those portions of your code are taking so much time. So the first question we can address with what we call time-based profiling. It's just a breakdown of what percentage of the time is being spent in each routine. Usually that's enough, but sometimes you need to dig a little bit deeper. So, so we could figure out how we can approach improving the code. So I'm going to be talking about two tools today. One of them is gprof, which is open source, widely supported. You could use it anywhere. The other one is uprof, which is going to be specific to AMD hardware, and you can use it on Expanse, which is an AMD-based system. But we're going to start with gprof. So gprof has a really long history. It goes all the way back to 1982. Which to me is just mind-blowing, because in the computing and technology space, 1982 is so long ago. That's 40 years old. And gprof is still one of the most useful tools out there. In fact, it's usually the first thing that I go to when I'm profiling a code. It is non-proprietary. It's not tied to any specific vendor or architecture. So you could use it on AMD, Intel. You could probably use it on ARM processors. You could pretty much use it everywhere. As far as I can tell, it has universal support by all of the major C and C++ and Fortran compilers. So I know that gprof is available for Intel, the AMD Optimizing Compiler Collection, the GNU compilers, Pascal, Portland Group. So you'll find it everywhere. It's also super easy to use. So some of the profiling and tracing tools have a steep learning curve. You really need to spend a lot of time getting up to speed on them. But gprof is kind of a snap. Really just 3 steps. You're going to compile your code with the -pg flag. Compiler flags tend to vary from one compiler to another. But this is one that seems to be pretty universal. Every compiler I've seen uses -pg. What that's going to do is when you execute your code, it's going to add some instrumentation to collect the statistics that gprof is going to use in order to generate the profile. Then you're just simply going to run your code just like you would normally run it. This is going to generate a gmon.out file. And then you run gprof, the name of the executable. Here I'm just calling it a.out and gmon, and you'll get your profile. And this introduces virtually no overhead. I've taken applications over the years. I've profiled them with gprof. And just as a check, I would see, what is the runtime of the code with gprof enabled and with it disabled. And if there's any overhead at all, it tends to be extremely, extremely small. Of course, when you're using the code in production, you'd probably want to turn it off. But if you forget, it's really not going to hurt you too much. Okay, so gprof is going to generate two profiles, a call tree and a flat profile. And these will all be output to a single file or to standard out. So the gprof flat profile, it's just a simple list of the functions and the subroutines ordered by their relative use. And in most cases, you're going to find that it's a small number of routines that account for a large majority of the runtime. So this is useful for identifying the hotspots in your code. Now, gprof won't zero in and tell you which lines of code are used most of the time. But if you're working with well-written code, I've heard, a good rule of thumb is that a particular function or subroutine shouldn't be much over 100 lines. It really narrows it down. You should be able to look at that, figure out where the time is being spent. Typically, it's going to be the innermost content of nested loops. So this is a result from a real application. It was from a collaboration that I did with the J. Craig Venter Institute a few years ago. They're right over off the corner of campus near the theater district. This was an application that was used for flow cytometry. It's a common lab technique used especially by immunologists to take cell populations and sort them into different types of lymphocytes that then break down into subpopulations depending on the proteins that they express on the surface. So when I first ran gprof, I was able to get this flat profile, and you'll see right at top, get number packed data. What was the routine that accounted for the majority of the time? In this case, it was just over 68%. And that was followed by the routine main, which is about 13%, and then quicksort double, that was 11%. So already we could see that, of course, we're going to start with get number packed data, move on to main, and then on to quicksort double. And then after that, there are probably no routines that are really worth spending our time on, since they account for such a minor portion of the runtime. You'll see in the second column, it's labeled as cumulative seconds. So what this is doing is it's taking the runtime for that routine and all of the routines listed above it. So it's basically summing it as you go along. And then the third column is self seconds. So that's the amount of time actually spent in that particular routine. So if we go to the second line for main, we'll see that the cumulative seconds is 687. The self seconds is 112.9. And if you take the 112, add it to the 574, you'll get the cumulative result, and so on. Well, let me just add, we got a pretty small group here, so feel free to post questions in the chat as we go along. I'll try to keep an eye on that, and I think Mary and Susan will also keep an eye. So if you see a good time to interrupt me for a question, just go ahead. All right, the second output that we get from gprof is what we call a call graph. So I find that I don't need to use this too often. I'll typically find that the flat profile really tells me most of what I need to know. But the call graph gives you some additional detail, such as the exclusive time spent in a function, the time spent in all the children's, statistics on calls from the parents. So what we're looking at here is the top of the the top of the call graph, there are many, many, many more lines. I'm just highlighting the first few. You'll notice we begin with main. So even though main didn't account for a very large fraction of the time, if you take main plus all of the routines that it calls, that's going to be on the top of the list. So basically, if we look at the inclusive time, we could see that main plus all of its children accounts for about 97% of the runtime. You would expect this to be 100. There's usually going to be a little bit of I'm going to say maybe a little bit of error in the percent time that's spent. This won't always add up to 100. gprof doesn't look at the level of every single instruction that's executed. Rather, it does a sampling. So there is going to be a little bit of variation, but it's usually pretty good. You'll notice that main is not indented, and then it's followed by a number of lines for get number pack data, is hump, quicksort, and so on that are indented. What this indicates is that we're looking at main, and then followed by all of the routines or functions that it calls. If you look at the second line for get number pack data, you'll see under called, it says 399.587/399.587. That means that the routine get number pack data was called a total of 399,000 times, and all 399,000 of those were by the routine main. We'll show an example later, kind of a toy problem that shows what it looks like if you have multiple routines that are calling a function. And then it's followed by 22,000 calls to ishump, one to quicksort, one to radix sort, and two to ID2 center. After that, we go on to the next routine that has the highest inclusive use, and that is get number pack data. You'll notice that main is indented above it. So that's the routine that's calling get number pack data. And then if we go down to the next block of output, we see that we're looking at is hump. Above that is main, because main was the calling routine. And after that is get nearest events, pack arrays, and pack points. So this is useful, especially if you find that functions or routines are being called by multiple parents. And in that case, you might find opportunities to, say, eliminate redundant calls to that function. Give me 1 second, I'm just going to turn off my email so that it doesn't keep interrupting me. Okay. Give me 1 second, I'm going to need to share again. Okay, let me just take a look at the chat. Okay, yeah, no questions yet. All right, but moving on. I'm going to talk about the value of reprofiling your code. So this was an application where I started off, I did the profiling. I started tuning the code. I dove into the routine get number pack data and was able to improve it a lot. And when I went back and reprofiled, I found that get number pack data was no longer the hotspot. So previously it had used 68% of the wall time. Now it's down to 26% of the wall time. And then previously, main had been using 13% of the wall time. But now that we were able to speed up get number pack data, the amount of time that we spend in main is a much larger fraction of the remaining runtime. So this means I may want to go back for another round of optimization. And in fact, that's what I did with this code. I then started working on the routine main and then functions that it calls. So we're going to look at a simple gprof example, and I'll show the code in the next slide. I know that but most of you are probably C, C++, Java, or Python programmers. May not have much exposure to Fortran, but I think that the code is simple enough that you'll be able to follow it. So I start with the main program, and it calls two subroutines, sub1 and sub2, and it's going to make two calls to sub1 and one call to sub2. And then sub1 is going to make n calls to function1 or f1, and also n calls to f2, and sub2 is also going to make n calls to f2. And n is going to be a variable that we pass to our executable on the command line. So to execute this, you look at the build step. In this case, I'm using the Intel Fortran compiler, ifort. So ifort-pg, the PG flag says that I'm going to enable gprof. I followed that by -march equals core-avx2. This is something that I needed to do with the Intel compiler on expense, so that the most advanced instruction set, the AVX2 instructions available on the AMD processors were used. -03 means I'm going to enable aggressive optimization, and then the name on my executable is going to be called intro. Then I'm going to run it. I use the Linux time utility to get the overall runtime, naming the executable. And in this case, I'm going to let n be equal to 1 billion. And then to generate the profile, it'll just be gprof, the name of the executable, in this case intro, followed by gmon.out, which would have been generated when I ran intro. And I'm going to redirect that into a file, profile intro. So to show you what the code looks like, this isn't the entire code, but I just pulled out the important snippets. In the main program, in the panel on the left, I'm going to allocate arrays, so W, X, Y, and Z. And they're going to be allocated to be of size n, the parameter that I'm passing in on the command line. I'm then going to initialize those arrays. For X, each element I, I'm just going to set it to I times 1.1. For Y, I divided by 3.3. And then I'm going to make the calls to subroutine 1 with one set of parameters, subroutine 2 with another set of parameters, and then sub2. And then if I look at the panels on the right, subroutine 1 is essentially a loop over calls to function 1 and function 2. Subroutine 2 is a loop over calls to function 1. And then function 1 and function 2, they just do some expensive operations. I'm calculating, they're doing a bunch of square roots and divisions. So like I said, the code doesn't actually do anything useful. It just takes up time, and it's a good, a good simple illustration of how we can use gprof. So I ran gprof, and the results didn't look like what we expected. So the runtime reported by gprof matches what we measured using the Linux time utility, but 100% of the runtime is attributed to the main program. So we're not seeing any usage data for sub1, sub2, F1, or F2, which I find a little surprising, because if we go back and look at the code, the main routine really isn't doing much. It's initializing a few arrays, it's making these calls to the subroutines, and that's about it. So what happened was that the compiler did an optimization called function inlining. So the first lesson that I think you want to take away from profiling your code is that an optimizing compiler may make transformations to your code that in extreme cases can render it unrecognizable. In this case, the compiler, like I said, it performed the function inlining. So what this does is it avoids the call overhead and allows the compiler to do additional optimizations. So in this case, the body of the functions, F1 and F2, were actually integrated directly into subroutines sub1 and sub2. And sub1 and sub2 were also inlined into the main program. So what we're seeing here is, these calls to sub1 and sub2 are going to be actually going to be replaced with the body of those subroutines, which are these three loops. And those function calls, F1 and F2, in turn are going to be replaced by the actual code for F1 and F2. Then the compiler is going to do the optimization on that transformed code. So that's why we see all of the usage here. If you look at 1, 2, 3, 4, if you look at the fifth line, you see that 100% of the usage is in main. So we're gonna go back. We're gonna do something a little bit different. We're gonna see what happens if we explicitly disable inlining. So I used another flag. This one is going to be specific to your compiler. And for the Intel compiler, it's -inline -level equals 0. So basically, when I use that in combination with -03, it tells the compiler, go ahead, do all of those aggressive optimizations, except for this one optimization, function inlining. I want to turn that off. So now things are going to look more like what we expected. If we look at the breakdown of usage, you'll see that that main really doesn't account for very much. It's about 6.25% of the time. That's just time spent in allocating those arrays and initializing them. Instead, you'll see that F1, F2, sub1, and sub2 account for most of the time, which is what we expect. F1 was at about 39%, F2 at 26%. Sub1 and sub2, even though they don't really do much, they're just making these calls to F1 and F2. They're going to incur a lot of there's going to be a lot of overhead, since they're repeatedly making calls to these non-inline functions. If we look down at the call graph, and of course in this profile we're not showing all of the output, just the interesting results. You'll see that main, for example, if we look at routine sub1, it's called by main. It makes 2 billion out of the 3 billion calls to F1, and then all 2 billion calls to F2. So now we're getting a breakdown of what we really expected the code to do. All right, so let me just point out one other issue with gprof. So the time that was reported for the entire program using the Linux time utility was 65 seconds. And in this case, it did not match what we saw for the gprof output. So gprof probably did a pretty good job of reporting where the time was spent, but it's not necessarily meant to give accurate timings. It's not a substitute for, say, measuring the overall runtime of the code directly. This could be done at the level of the entire program, like I did with the Linux time utility, or by inserting instrumentation timers into your code. And this is something I won't get into it here, but you will see this in a lot of the well-supported third-party applications. They may give you a breakdown of where time was spent in different operations, and that was done by the programmers manually inserting timers to say you spent this much time in this routine, this much time in this operation. I mentioned that gprof really doesn't add much overhead. I looked at examples here where I looked at the 4 different cases, compiling with and without the -pg flag, and with and without inlining enabled. And if we look at that second column of the table, inlining enabled, the runtime was 18 seconds in both cases. With the inlining disabled, we saw a little bit of a difference, 65 seconds versus 62. That's not much overhead. And also this code is a little pathological because we're making many calls to functions that really don't do very, very much work. But generally you're going to see that that gprof adds very, very little overhead. Now, this isn't necessarily the case with some of the other profiling tools out there. There's a really fantastic tool called Tau, which is used more for analyzing parallel applications. determining where the where the bottlenecks are, identifying the patterns of communication, which actually adds quite a bit of overhead. And then Tau will try to estimate what that overhead is and subtract it out, but it's not quite accurate. But either way, you're still going to get you're still going to see a big impact on the performance. All right, so before I go on to uProf, are there any questions on gProf? And since we have a small group, just feel free at this point to unmute and ask a question. Okay, if not, I'm going to go on to uProf. So I think uProf is a more interesting tool. There's a lot more you can do with it. But again, it's specific to AMD hardware. It is a proprietary tool. You won't be able to use it on other systems that are, say, Intel based. Instead of using the -PG flag, you're going to use the -G flag. This is the debug flag so that you get symbol information, which will allow you to actually get usage at the level of the source code lines. uProf is going to generate the profiling data in two formats, much harder to read than the gProf output, but then it's also much more comprehensive. It will give you a CSV file that's human readable, and I'm going to recommend that you just open this in a spreadsheet. And it also generates a SQLite database that can be imported into the AMD uProf GUI. In addition to time-based profiling, which is what we did with gProf, you can also access these low-level performance counters to investigate things like cache usage, branch prediction, and other low-level information. And we'll give an example a little bit later showing how this could be useful. So when we use uProf, there are going to be three steps that we take. There's what we call the collect step, which is where we run the application program and collect the profile data. There will be the translate phase, which is where we process that profile data to aggregate and correlate and save them into a database. And then finally, there's going to be an analyze step where we view and analyze the performance data to identify the bottlenecks. So uProf collect, to start with the collect phase, we're going to use the AMD uProf CLI-bin tool with the collect command. When we do this, we can specify what kind of sampling we want to do. There are predefined profiles, and I'm going to show these on the next couple of slides, or we can select specific events, dive into particular counters. I find though that the predefined profiles, unless you need to do something very, very specialized, actually work pretty well. And there's one in particular that we're going to be using today. I think the name of the tool is a little unfortunate. AMD uProf CLI-bin doesn't exactly roll off the tongue. But if you load the uProf, I believe it's the uProf module on Expanse, you'll get access to this tool. So after I've compiled my code, I'm going to use AMD uProf CLI-bin. I'm going to specify collect. Then it's going to be followed by --config sampling. That's the type of sampling we want to do, and I'll show a few examples of that. -O output. This is where I want the results to go, and then followed by the name of my executable and any command line arguments. So if you're on a Linux system, this is going to generate an output file, output.caperf. Or if you're on Windows, it's going to be output.prd. And these are not human readable, but they're going to be used in the translate stage. Of course, Expanse is an AMD-based system, so we're going to be getting the former, the caperf file. So I mentioned earlier that uProf has predefined profiles for the collect config option. The first one we're going to look at is what we call time-based sampling. And that's the first one on my list here. And we use this to identify where programs are spending their time. The output that you're going to get if you use the TBP configuration option is going to be very similar to what you get out of gprof. Essentially, it's a profile of which routines are using the time. There are a bunch of other profiles. I'm not going to get into the details here, except to mention data access at the bottom. This is the one that you're going to use to find data access operations with poor L1 data cache locality or poor data translation look aside buffer behavior. So basically, you're getting at how well you're managing the data, and I'll get into that a little bit later. We have an option for investigating branch prediction. Going a little bit deeper into performance. You'll notice for each of these that at the bottom, except for the time-based profiling, that we have these PMU events, and I forget what PMU stands for, but these are followed by a bunch of event codes, PMC, followed by a 3-digit hex code. These are the names of the specific AMD counters. And they're going to correspond to things like L1 cache misses, L2 cache misses, L3 cache misses, missed branch predictions, and other low-level information. We can also, we can do instruction-based sampling. We can do an analysis of the cache. I find that these aren't nearly as useful, though, for most applications as simply the TBP and the data access. Okay, so, good question. I see it here from Will Castillo. Is this the same thing as tracing? No, tracing is, I think tracing is something more that you're doing with parallel applications where you're keeping track of when various events are occurring. Say when a message is issued during message passing, when processes are waiting, waiting to reach synchronization points. Yeah, so this is something that's a little bit, I'm gonna say not lower level, but specific to the underlying serial application. All right, getting into one kind of nerdy detail, and this is a note on paranoid levels. And this is something that I ran into when I first started using uprof. The type of profiling that you're allowed to do depends on the on the value of the perf event paranoid setting on the Linux system. This is something that you don't have control over. Our sysadmins are going to set the paranoid level. So in order to use all of uprof's predefined profiles, we would need to set that paranoid level to value that's so high that it introduces security risks. If you're really interested, you can take a look at these threads on Stack Exchange and Stack Overflow. The folks that do cybersecurity are really sharp, and they've noticed that there are ways that if a user is given access simultaneously to too many of the performance counters, that it opens up security holes and they could actually hack the system. So what we're going to be doing is, I talked to our systems group about this, is that we found that a good balance between security and usability was to set the perf event paranoid level to 1. And that's going to allow you to do time-based and data access-based profiling. And you can also access specific counters. The problem is, if I go back and I look at, let's say, branch prediction, the number of counters, there are eight separate counters that are being accessed. That's over the limit for what's allowed with our default level for the paranoid setting. I believe that the way we have it configured allows you to access 6 of these performance counters. So I'm going to direct you, if you're really interested, you could take a look at the documentation for uprof and specifically request in individual counters to get at that information. But again, most of you are going to be doing time-based and data access profiling. Let me just 1 sec. All right, so the next step is going to be what we call the translate step. And this again is going to be done with the AMD uprof CLI bin tool. But in this case, the first argument, instead of being collect, is going to be report. And it's going to take as input that CA prof file that we had generated previously. I have here in angle brackets output. That's going to be the same output name that you specified during the collect step. After you run this is going to generate a new directory named output, and that's going to contain 2 files. There's going to be an output.csv and an output.db. So the former is plain text, which you can then take, either read directly or maybe to make it more useful, dump it into an Excel spreadsheet. While the latter is a database file that's read by the uprof GUI. So profiling data, it could be analyzed anywhere. Well, once you've generated, you no longer need access to the compute node. You could download that data to your laptop. You could look at it in the login node in Expanse. My preferred way of doing this would be to take the database and read that by the AMD uprof tool, the GUI, on my local machine. And I realized that this slide may be out of date. The last time I gave this presentation, AMD did not currently have an implementation for Mac. So if your laptop is a Windows system, you should be able to use this GUI. In my case, since I have a Mac, I was stuck with pasting the output into Excel. Works pretty well. Just need to do a little bit of formatting, column resizing, and familiarizing myself with the output. Okay, so we're going to go back. We're going to revisit the first example that we looked at with gprof, except this time we're going to use uprof's time-based sampling. Instead of using the -pg flag, we're going to use the -g flag to get symbol data, and get rid of the -pg since that was specific to gprof. So the 3 steps, we're going to start off with build. And using I4, we're specifying the architecture. We can do it with or without inline level set equal to 0. We then do the collect stage. This is what we call the AMD uprof CLI bin tool. First argument is collect. We're setting the configuration to time-based profiling with --config TBP. We're then going to call the output intro_inline -TBP. And then I'm going to execute the code. And this, again, we're going to set the input, the command line parameter to 1 billion. And then we do the translate phase. So again, AMD uprof CLI bin, in this case, report instead of collect. And I'm going to specify as input the CA perf file that I had just generated. Okay. And then this is what the output is going to look like. I know this is going to be hard to read here. Maybe if you download slides and look at this later. But at the top, you're going to get information on the execution environment. It's going to tell you things like the kind of sampling that you were doing. When you started the profiling, when you ended the profiling, it will give you the target to the executable, command line, arguments, and so on. I find this is really, really handy because when I use gprof and I look at that profile, I need to go back and think about which problem did I run? Which executable, which command line arguments. And this is nice because it collects all of that information for you. Next, it will be followed by a section they call hot functions. And this is a lot like the flat profile that you get at gprof. It will give you a listing of the functions that are using the order from top to bottom that are using the most time. And then you'll get function detail information. And this is where it gets a little more fine-grained, and it tries to assign CPU usage to individual lines of code. So if I look at the results for the time-based profiling with inlining enabled, on the left panel for hot functions, I'll see that main accounts for the vast majority of the runtime, followed by a bunch of which are really lower level system calls. And then on the right panel, you'll see uprof's attempt to assign usage to individual lines of code. So this needs to be taken with a grain of salt, because as code is optimized, especially if they're going to be loop level transformations, the source code won't really transform precisely to the optimized code. But here, though, you can see that most of the time was spent in main, and the breakdown was about 4 seconds or almost 5 seconds being spent in function F1, 7 seconds in function F2, and smattering of time for other lines of code. Now, if we go back and we did the same thing we did with gprof, except this time disabling inlining, we'll see that that the time is actually spent where we expect in functions F1 and F2, and then a little bit in subroutine 1 and subroutine 2. Note, though, that if we look in the right panel, that the assignment of time to lines of code isn't quite right. So if we start with those top lines in the right panel for function F1, you would expect that most of the time would be spent in that one executable routine in the function. F1 equals square root of x divided by square root of y plus y over x. What we find, though, is that uprof assigned the majority of the usage to the end function F1 call. So if this were C code, that would be the equivalent of assigning usage to a closing parenthesis. If we look at F2, it seems to have gotten that one right. Most of the time is being spent in the line that actually doing the work, and then a little bit in the end function call. So again, the takeaway here is, don't quite believe the results for the assignment of usage to particular lines of code. So we're going to get into uprof data access profiling, but we need to do a little bit of digression first. So although gprof can tell you which functions are taking the most time, it may not give you a lot of insight into why a particular function is expensive. So if we have codes with low computational intensity, and by this I mean that we do relatively little computation for each word of data that's operated on, performance is going to depend very, very heavily on how well we manage data movement, and in particular, how we make use of cache. uprof gives us access to program counters, which we can't get in gprof, and it's going to let us go a little bit deeper. So, let me go through, take about 10 more minutes. I'm going to go through the memory hierarchy, and then we'll take a short break. My dog is standing behind me, and she's beginning to complain it's time for dinner. So memory-bound codes. These are codes in which the rate at which data can be delivered to the CPU is the limiting factor. And our goal is going to be to apply cache-level optimizations so that the CPU is not starved for data. In compute-bound codes, it's really the performance of the processor that's the limiting factor. So we can get the data to the CPU fast enough but the processor can't keep up. So our goal is going to be to, in this case, to reduce the amount of computation done on a given piece of data. In real applications, though, we're going to find that we have to deal with a combination of compute-bound and memory-bound kernels. So those of you who are coming from computer science, you've probably seen a figure, something like this at some point. That this is the computer memory hierarchy, usually shown as a pyramid, because at the top we have registers, which have very, very small capacity. I believe that register counts for modern processors are measured in the tens of registers, all the way down to the bottom of the hierarchy, which is storage, disks, hard drives, solid state drives, and maybe even tape archives. So as we go up in the hierarchy, data access is faster, but it's also smaller and it's much more expensive. Before we had cache, there was a much flatter hierarchy. We had registers, we had DRAM, and then we had disk. But we noticed that there are certain patterns of data usage. So if we can take data from DRAM and move it into this very fast memory that we call cache, that we can really improve the performance of these memory-bound codes. So cache is actually on the chip. If you look at pictures online of processors, sometimes they'll be annotated showing, which part of the die is used for different functions. Overwhelmingly, the largest allocation of space in that die is for cache. And we will normally have 3 levels of cache. There's an L1 cache, which is on the order of tens of kilobytes. Data there can be accessed in a few clock cycles, so on the order of nanoseconds. We have an L2 cache, which is larger and a little bit further away from the registers, and then an even larger L3 cache. When we have data in register, it's immediately available for use by the CPU. So what we want to do is we want to exploit 2 cache essentials: temporal locality and spatial locality. So for temporal locality, the idea is that data that was recently accessed is likely to be used again in the near future. So to take advantage of temporal locality, once we load data into cache, we keep it there until it has to be purged to make room for new data. The idea behind spatial locality is that if a piece of data is accessed, it's likely that neighboring data elements in memory will also need to be accessed. So to take advantage of spatial locality, cache is organized into lines, typically 64 bytes, and that entire line is loaded into cache at once. So our goal for the cache level optimization is going to be to exploit both temporal and spatial data locality so that we can minimize data access times. I know that this figure is pretty busy, but I'm going to be coming back to it a little bit later. Since main memory is much larger than cache, we need a policy for taking locations in memory and mapping it into the cache. And this is done in a very predictable way based on a portion of the memory address. Most modern CPUs are going to use something that we call set associative cache, where a piece of memory can map to multiple cache lines, but again, in a very specific way. So what we're showing here is a 2-way set associative cache. Modern processors, though, will have much higher set associativity. I believe it's now like 64 or 128. So caches also need a strategy for discarding old data to make room for new data. And this is done by some variation of what we call a least recently used algorithm or random replacement. For those of you who are in CSE, you may have already taken or probably will take a class in computer architecture that will dive way deeper into cache. So how does this relate to code? Let's consider a one-dimensional array. So a 1D array is stored as a block of contiguous data in memory. So if I look at this little snippet of C code where I'm going to allocate 100 4-byte integers, they're going to be laid out contiguously in memory. So the first element, x0, is going to have an offset of 0 bytes. X1 will be offset by 4 bytes, x2 by 8 bytes, and so on from the beginning of the array. So if we're trying to do cache optimization for a 1D array, this is going to be really straightforward, and you're probably going to write optimal code without even trying. Just access the elements in order. So what's going to be happening under the hood? If I look at this snippet of code where I'm incrementing the 100 elements, sorry, incrementing all the elements of array X, just adding 100 to them. I'm going to start off, I'm going to load elements x0 through x15 into cache. I'm then going to increment x0 through x15. Then I'm going to load the next 16 elements, 16 through 31 to cache, and then I'll increment those elements. But processor designers are really, really clever. And what they're going to do so that I don't necessarily have to wait for that data is that processors can recognize the pattern of data access and prefetch the next cache line before it's needed. So one of the questions that often comes up is, do I have control over cache? Can I say, I want to load this data into cache? And as far as I'm aware, there are no programming constructs in the higher level languages that give you direct control over the cache. So for example, load this particular location in memory into cache. That's probably a good thing, because if you started doing that, your code would become, would be very non-portable. It would end up being extremely specific to that hardware. And it's also likely that you would do a worse job than the cache replacement strategies that are implemented in the processor. So the best that you can do is to follow the standard practices to exploit temporal and spatial locality, and in some instances, choose optimal parameters, say array sizes, based on the properties of the cache. So now we're going to consider multi-dimensional arrays. So 1D arrays are pretty simple to work with, but what if we have 2D arrays? So from a computer's point of view, there is no such thing as a 2D array. This is what we call syntactic sugar. It's just the convenience of the program. So under the hood, that multi-dimensional array is going to be stored as a linear block of data. And here's where it gets a little complicated. There are two different conventions. There's something that we call column major order. The first or the leftmost index varies the fastest. And this is what you'll see in Fortran and R and MATLAB code. So if I have this 2D array of numbers 0 through 15 laid out as shown in the top here, I'm going to go down the first column. So it's going to be 0, 4, 8, 12, 1, 5, 9, 13, and so on. Row major order is where the last or the rightmost index varies the fastest. And this is used in Python and Mathematica and C and C++. So I'm going to go across the rows, 0, 1, 2, 3, 4, 5, 6, 7, 8, and so on. It would be nice if all the programming languages use the same convention. Unfortunately, they don't, and this is really, really locked in. To me, a good analogy would be, which side of the road do you drive on? Of course, here in the US, South America, Canada, most of Europe, we all drive on the right side of the road. You go to the UK, India, Australia, and so on, they drive on the left side, and nobody's going to change. This is pretty much locked in, and you just have to be aware of this. Make sure that you're aware of the convention for the language that you're working with. So let's say that I need to do an operation where I'm adding two arrays, element by element, and storing them in a third array. Properly written Fortran code. Notice that I'm doing a do j, do I, and then I have the operation in the innermost loop, zij equals xij plus yij. Note the loop nesting. I have my innermost loop corresponding to the leftmost index. In the next example, for properly written C code, I'm going to flip things around. I'm going to have for I, then for j, then zij equals xij plus yij. In this case, my innermost loop corresponds to the rightmost index. And you're going to see in our example that we're going to get to right after the break, that getting the correct that having the correct ordering of the correct nesting loops when we work with these multi-dimensional arrays is going to have a really big impact on performance. So with that, I see we're at the top of the hour. Why don't we take a 5-minute break, and then we'll come back and we're going to look into using uprof to analyze cache behavior. So any questions before we take our break? Alrighty, so short break and see you in about 5 minutes. Oh, great! I see a question here from Alexander Millar. About what's special about 32,768? Because the end of the inner outer loops hit limit of signed integer short, or what? I had never thought of that. But if that were the case, we would have expected, I think, to see similar behavior for 32,769. But I will get into that, for what I think is the explanation in the next couple of slides. Alrighty, so why don't we kick things off again? Susan, recording is still going?
It is, Bob.
Okay, great. All right. So we will finish up here. I know this is some pretty heavy material for a Friday afternoon. But thanks for bearing with me. Okay, so we're going to look at an example of a matrix addition code. This little piece of code doesn't do very much. It just allocates 3 large matrices, initializes 2 of them, and then adds them element by element. We're going to be working with some pretty big matrices. When you do this experiment on your own on Expanse, you'll probably want to grab an entire node because this is going to use a lot of memory. So I have a table here showing the runtime for the addition of these n by n matrices, so roughly the 32,000 by 32,000 matrices. When I use proper loop nesting and the improper loop nesting. So let's start with the first row, n equal to 32,767. We see that when I use the correct loop nesting, so that we're accessing all of the elements in of that multi-dimensional array in the proper order. It takes a little over 2 seconds. When I have the improper loop nesting, it takes almost 30 seconds. So that's close to 15 times slower. So this is a great illustration of how doing data access correctly in an optimal order can really impact the performance. Now you notice in the second column, the time for the proper loop nesting, it really doesn't vary as I make small changes to the size of my matrices. So when I go to 32,768, just a smidgen longer, probably within the noise. 32,769, just a little bit slower than 32,768. But when I look at that last column, I go from 29 seconds to 124 seconds, and then down to 21 seconds. So something really interesting is going on here. So this would be a great time to use uprof to do data access profiling. We don't need to do time-based profiling with this code because it's just one routine. You'll see this when you go into my GitHub repo. And we already know where the time is being spent. It's in that matrix addition. So instead, we're going to do data access profiling to get a deeper understanding. So we're going to build the code. In this case, I use G-Fortran. I have source code files named dmad_bad and dmad_good.f to indicate that I'm using the good or the bad loop nesting. So I do the compilation. I use the AMD uprof CLI bin tool with the collect option. And in this case, I'm going to set the configuration to data access. And then I do the translation. So what I find when I look at the output from uprof using data access is I get information on cache behavior. So what I'm showing in the table now is the number of cache misses. So when I use the proper loop nesting, they're around 10 to 11,000 cache misses. When I use the improper loop nesting, it's much higher. At 32,767, it's about 195,000. At 32,768, it jumps way up to almost 1 million cache misses. And at 769, we're back down. In this case, actually a little bit lower than when we used 32,767. So we know what's going on here. We know why the code with the proper loop nesting is so much more efficient. It's making better use of cache. It's loading that data into cache. It's making use of that entire cache line. When we have the improper loop nesting, recall that the size of our matrices is so large that it's not all going to fit into cache. So we load data into cache, and then we have to push it out to make room for additional data before we had a chance to use all of the all of the elements in that cache line. So, but the mystery though is still, what's special about 32,768? And many of you probably recognize that it is a large power of 2. And this gets back to the way that memory is mapped to cache. So the algorithms will use a portion of the memory address to decide which cache line it goes to. When we use n equals to 32,768, we're accessing the data with a very large stride, and we were constantly, probably every time, pushing data out of cache. So not only were we having bad data access, we also picked a bad problem size. Now for the case of doing this matrix addition, if that's all we're doing, it's very easy to just nest the loops in the right order to get the best performance. Sometimes though, you may be stuck. You may have to work with how do I put it? You're working with multiple arrays, and there may be no way around having to access one of those arrays in the wrong order. Let's say that you're adding a matrix to a transpose of another matrix. But what you could do though is when you see this kind of behavior, and you see not only the increase in the runtime, but an increase in the data cache misses, that you could maybe alter your problem size a little bit. Or if you really wanted to work with arrays of size 32,768, you might want to pad your array and actually use the pack that into a slightly larger array, allocate it to be larger, but not use all of the elements. So there are different strategies we could take, and this is the kind of insight we get by doing an analysis of cache usage. All right, so we are almost done. Just want to talk about where to go for help. And I know this is a really minor point. I think it was a little unfortunate the way that AMD named their tool. Is it uprof or is it muprof? And AMD tends to use these two names interchangeably, sometimes on the same web page or the document. Google searches for uprof and muprof seem to yield the same hits for the official AMD pages, but different hits for the non-AMD pages. So on the left, I did a search for muprof, and on the right, I did the search for uprof. And you'll see that the top two hits are the same. But when I go a little bit deeper, you're going to see that muprof and uprof return different hits. It looks like muprof is more reliable. In the panel on the right, those next three hits, the first one was actually to the AMD tool. The next two were to something that was completely unrelated. So, if you're looking for information on uprof, I would say search both, but searching on muprof is probably going to work a little bit better for you. Okay, and with that, I'm just going to wrap up to tell you about some exercises that you can do on your own. Again, if you go to the GitHub repo that had been pasted into the chat multiple times, the one that corresponds to the that corresponds to my personal GitHub account, you will see the code and the output for these examples. It also includes the commands that you're going to be executing. So I'm going to say, run the gprof example with the intro.f code and convince yourself that you understand the output. And then maybe modify functions f1 and f2 to use sines and cosines and log functions instead of square roots, and see how that affects the gprof output. One hint is you're going to see a lot of references to something called SVML. So you can go ahead and Google that. So these functions are very expensive and they can lead to longer run times. So you might need to shrink down your problem size a little bit. And then you could also look into the compiler's inlining capability. So right now it's easy for the compiler to do the inlining because all of the code for the main program and the subroutines and functions, it's all in one file. But see what happens if you break that up into 2 files, or even into 3 files. In the third case where you have the main program, the subroutines in one file, the functions in another. And then you could also explore other compilers, the AMD compilers, AOCC, Flang, and GCC Fortran. For uprof, see a comment from the chat. Good question from Will. If you compile without -03, will it also disable inlining? That is going to depend on the compiler. So first of all, the default optimization level for compilers varies. So if you use the Intel compilers, the default optimization level is -02, and I believe that it gets you function inlining. I believe for the AOCC compilers, though, that if you don't specify an optimization level, you get -00, which is absolutely no optimization, in which case it will definitely disable inlining. But again, it's where inlining occurs as a function of optimization level is going to be compiler dependent. Right, so getting back to the uprof example, I'm going to say, good homework would be follow this link, read the uprof user guide, and then profile intro.f using time-based profiling like we did. See what happens if you omit the -g flag. You could do the same things that we talked about for gprof with breaking up the code into multiple files, modifying the functions so they use more expensive routines, explore other compilers. And then for matrix addition example, you could reproduce what I did, and then also play around, look at the effect of the problem size. Do we see the same behavior for other large powers of 2? Or what if we do something, dimensions that aren't a power of 2 but contain large powers of 2? So a lot of tinkering you could do. And with that, I'm going to wrap up the official part of the presentation. There's a lot of extra material that I included here. We call this supplementary material on performance optimization and tuning. So if you go through here, you'll see a lot of, well, it started off kind of with the philosophy of profiling code. What you see with different compilers, and then the types of loop level optimizations that you can do. So with that, I'm going to stop sharing. And just give me a minute. I'm going to pull up my GitHub repo. Just bear with me for one moment. Sorry, wrong repo. Give me just one moment. Okay, so you should all be seeing my browser. I went into my profiling tutorial. You see there's a README, just a few words in there. I have the slide deck, which I just used today, and I updated that earlier this morning. So what I presented is consistent with what's in my repo. And then there's, the code and the commands for doing the time-based sampling and for the data access sampling. And I've included the commands, showing you which modules to load and how to compile the code and execute necessary commands. So I think everything that you need will be there in that repo.